All right, welcome. In this video, we're going to talk about paper chromatography, and we're going to look at the results of our lab. So let's first take a look at this, our lab data. So I'm going to pull up the video of this lab that we did. Hopefully this will work. Okay. So what happened in this is some time-lapse photography. Let me start this over. And what we did is I put water in this flask over here to the left, and we put isopropanol in the flask over here to the right. And then we drew a line with a pencil on this paper. This is chromatography paper, and which is kind of similar to like coffee filters. That's a similar type of thing. And then I put the sample on it, which in this case our sample was a like a washable brown pen. Okay, like a vis-a-vis marker, so a brown pen. And then we kind of let this go for about 25 minutes. And you can see that the liquid, so the water on the left and the isopropanol on the right, they're starting to move up the paper. And as they kind of move through the sample, they're dragging kind of bits of it along with it. And notice how the sample is separating. So chromatography is what we call a separation technique. So it's allowing us to see, for example, that my brown pen is actually made up of 3 different pigments. I can see there's blue, yellow, and like a red, pink in there. Okay. So we see it moving up the paper. Also notice that the water is moving faster than the isopropanol. So right now the water is all the way up here. The isopropanol is only down here. That's due to the stronger intermolecular forces within the water. So the water can kind of attract to the paper, and then it attracts other water molecules, and they kind of then gradually they work their way up the paper due to all those various forces of attraction that are stronger over here than they are in this sample. All right, so then we pause it and then we take some data. So let's take a look at what this data will look like. So notice down here, this is our pencil mark. And this right here is the starting point. And so that's where, when we're taking measurements, that's where I put my ruler at 0. I know it's kind of, perspectives might be a little hard to read, but that's our ruler. 0 is the starting point. That's the pencil. And then we want to look at the distance the water traveled. So you might notice over here that this part of the paper looks wet. So we can kind of tell that this is about how far the water traveled. And so I'm going to say that that's maybe 7.6 centimeters. And maybe we're making different judgment calls. I'm not expecting we're going to have the exact same numbers here. So maybe you said 7.4 or 7.5 or 7.7. Doesn't really matter. But that's about how far the water traveled. And let's look at the red pink dye. Again, we're going to get different numbers here because it's kind of a smudge. But I'm going to say that the red dye maybe traveled to about there, which to me is looking like 5.4. And honestly, every time I look at this, I'm getting slightly different numbers. That's okay, right? That's why this digit is the uncertain one. So yeah, so maybe you said 5.3 or 5.6. That's fine. Yellow is maybe right around here. It's kind of a little more wobbly, so it's a little harder to judge that one, but I'm gonna say maybe 6.6 centimeters. And then I'm gonna call the blue one as being maybe like 7.2. All right, and then we're going to calculate the retention factor. And it talks about the retention factor in your notes here in the lab handout. So basically it's the distance traveled by the compound divided by the distance traveled by the solvent. So that is how you find the retention factor. So let me maybe snip that and put it over here. Oh, maybe I can't snip it here. Okay, anyways, so that's how we find the retention factor. So so basically it's the distance traveled, like in this case, it's the distance traveled by pink, which is 5.4 centimeters, divided by the distance traveled by the solvent, which is 7.6. And notice how it's centimeters divided by centimeters, so that cancels out. So this answer is just a ratio. It's just a kind of a unitless number here. So 5.4 divided by 7.6, and this is 0.71. And then this one is 6.6 divided by 7.6. And again, we will get different answers here because we're reading the ruler a little bit differently. There is some inherent, uncertainty in these measurements here. So if you're getting something slightly different, don't change yours to match mine. As long as we have the right general idea, we're okay here. And I rounded my answers to 2 sig figs. That seems to match my measurement just fine. And one way you can think about RF, that stands for retention factor. And you can think of it as like how well the solvent retained the pigment. So like one way you can think of this one is if I'm looking at this data, we're looking at the solvent here is water, and it looks like my water solvent retained the blue about like about 95% retention. So the blue basically stuck with the water all the way. Whereas like the red pink one was only about like 71% retention. So it traveled more than half the way with the water, but it didn't stick to the water as well as the blue did. And then the yellow is kind of somewhere in between. That's how I might interpret those retention factors. And so if we're looking at the results here, the blue dye traveled the furthest in water. It had the highest retention factor. And so if we think about what that means, in the chromatography, we got 2 phases. We've got the stationary phase and the mobile phase. The water, the solvent, is what we call the mobile phase. That's the one that's moving up the paper. And then the stationary phase is the paper. The paper is just kind of staying still, right? And so the blue traveled the furthest. That means that it stuck to the solvent, your water, more than it did to the paper. So it's more attracted to the water than it is to the paper. Okay, because it was retained really well by the water. So there's a strong attraction between the water and the blue dye. So we can ask some questions about, what does this tell us about the, relative polarity, maybe intermolecular forces that the blue dye experiences. And if you look at the various substances involved in this lab, this experiment we're just looking at, we've got water, we've got the paper, which is made of cellulose, and then we've got isopropanol. And they're all somewhat polar, but water is the most polar of them. And then cellulose is kind of in the middle, and then isopropanol is the least polar. And what you will notice is that the blue dye traveled really well with the water. That means it's got a really strong attraction to water. It's more attracted to water than it is to cellulose. So the blue dye is attracted to the most polar substance. Therefore, we can say that the blue dye must be fairly polar. That's the kind of conclusions we want to draw here. Notice that the blue dye traveled really well in the water. It didn't travel as well in the isopropanol because the isopropanol is not as polar. So if you look at a polarity map of this one, you see how water is like all basically red or blue. So it's got a positive side and negative side, and it's like super polar all the way around. Isopropanol is polar, so it's not symmetric, right? There's an O and an H over here. So it is polar. There's some positives and negatives in it, but a large part of the molecule is actually shaded green, which means it's neutral. So a lot of this is actually non-polar. So all of these substances, all these molecules are polar, but some molecules are more polar than others. And water is like the most polar of these substances. So it's just important to notice that it's not like, a yes or no dichotomy. Are you polar or non-polar? It's actually a spectrum. You can be either like very polar or somewhat polar. And so that's just kind of important to keep in mind in general as we're thinking about these molecules. So as you're trying to interpret your results here, you can think about the force of attraction to the mobile phase and the stationary phase. And another way of thinking about it, which you might find simpler to kind of wrap your head around, is to think of your chromatogram, which is like your results of chromatography, as a measure of the solubility of a substance in the given solvent. So the one that dissolves the best in the solvent will travel the furthest in the solvent. So in this example, you've got like 3 pigments. It looks like pigment B traveled the furthest. So we'd say that pigment B is the most soluble in whatever your solvent is. And pigment C is the least soluble. Okay. And so it's super important here when you're trying to interpret your results then to consider what your solvent is. So if your solvent is polar, then your polar substances are going to dissolve really well and travel the furthest. If your solvent is nonpolar, then your nonpolar substances will dissolve well and travel the furthest. So pay attention to your solvent. That's one of the most important things when you're interpreting chromatograms, right? When you're interpreting your results here. So here is a side-by-side scenario. So if you want to pause this video and think about this, we've got scenario 1 where we're doing a chromatography using hexane as the solvent, which is nonpolar. And over here, we're using water as the solvent, which is polar. So let's think about scenario 1 first. So A traveled the furthest. So it was kind of retained the best by hexane. So this one, dissolves better in hexane. And since hexane is nonpolar, that makes me think that A is relatively nonpolar, which means that B must be more polar. So based on this data, B seems the more polar of these two options because it does not dissolve as well in the hexane. Over here, X, seems to dissolve better in the solvent, which in this case, the solvent is water, which is polar. So that tells me that X is the more polar of the two. And since Y does not dissolve as well, it is the less polar of the two. So in this case, X is the more polar. So when you're interpreting your results and looking at the distance these various things travel, it's super important to think about what the solvent is. Because if the solvent is nonpolar, then traveling further means you're less polar. But if the solvent is polar, then traveling further means you are more polar. So again, pay attention to what the solvent is really key. And if you notice, we can kind of see the impact of this in our lab if we compare what happened in the isopropanol versus the water side by side. So notice that our pink-red pigment, it traveled the furthest in isopropanol, which is our less polar solvent, and it traveled the least far in water, which is our more polar solvent. So based on this data, it seems like our pink pigment is the least polar, of the three pigments we're looking at. So if you're comparing like, pink and yellow and blue, our pink one seems to be the least polar because it was the least attracted in water and it was the most attracted in isopropanol. So that's how we kind of want to interpret our chromatography data. And let me know if you have any follow-up questions.